And there's another time when you could expect action and get it, too. I'm talking about my new Ford Thunderbird.
My name is Prince Jamil Brahma. I am a energy engineering student at Penn State University. On this video, I'll be showing, discussing, and creating the tail lighting system for the 1965 Ford Thunderbird. The actual car's taillights, but instead, I'll be showing a demo representation of the actual tail lighting system and how it works, and different components and pieces needed to create it. I'd like to say this video is intended for advanced high school engineering students and college engineering students as well. But before we start, let me explain the uniqueness of this tail lighting system. Ford Thunderbird models have always had unique and distinct taillight designs and systems compared to any other car model. It all started from 1955 to 1957 when they brought out the Hollywood Thunderbird with the turbo style lights. Then they switched to the three taillight system that continued into the 70s. And then they brought out the insignia encrusted Thunderbird. And last but not least, the single trunk length lights in the late 1970s. But that's not our concern today. Our concern is about the most unique out of all of them, the three taillight system on the 1965 to 70s models. The three taillight system follows a very distinct pattern that can also be seen on the '05 to '09 models of the Ford Mustang. It is a sequential pattern, as you can see in this video, as the first light turns on, the second following, and finally the third, and the pattern restarts. As simple as this pattern sounds, to recreate it on an actual circuit board is rather tedious, so we'll go step by step on how to recreate this pattern and recreate it on an actual program and play a demo version of it. So the first step in recreating this complex circuit for the tail lighting system is first creating a timing diagram. For those of you that don't know what a timing diagram is, diagram is basically a way to line up your results with a time-based circuit. And this is a time-based circuit. Basically, every second counts. You need a different result from the previous second. So everything is all time-based. So I mapped out a timing diagram for this circuit, and let me go through it with you. Now, first, we want everything from the clock to all three outputs to be on low or zero. Basically, nothing should be happening in the circuit uh, when nothing is happening. Nothing should be going on. But as soon as we turn on the circuit and we flip our switch, and the clock starts running, the first pulse that the clock hits high, the first light should be coming on, and the other two lights should be remaining off. Now for the second, as we approach the second, notice how this remains high until the second. That's what we want. When for this tail lighting system, we want the first light to remain on until the third light comes on. So we just need all the first light to just remain on throughout the whole time until the third light comes on. So when we reach the second second, the first light should remain on, and now the second light should be turning on. The third light will remain off. As we approach the third second, this is when, just like the first light, the second light should be remaining on for the duration. So as we approach the third second, this third light should be turning on, and all three lights should be on at the same time. Now is the difficult part. This fourth second, after the next clock pulse hits high, all the lights should be off. They should all immediately turn off. Not one light, not two lights, but all three lights should be off. And in the following second, the first light should be turning on again and restarting the pattern. So this is why it's so important to make a timing diagram first, so you can have an idea of how the circuit should be working based on each second. So I'm going to explain our first component that we're going to use, which is a D flip-flop. May I add a positive trigger D flip-flop. Now, a D flip-flop, the reason we're using it is because the D flip-flop is very convenient for the circuit that we're going to recreate. The D latch will respond during the entire time the clock input is high, or 1. When the clock hits low, or 0, the D latch will remain in the last state, or last memory, or the last input that was in. So that may be a little confusing, so I drew this state table to further explain it. So as long as the clock input is high or 1, whatever D is, or whatever that input is, that's what this output shall be, or Q. So if D is 1, or the input is 1, that output shall be 1. If the input is 0, that output shall be 0. But if the clock hits 0, Q, or the output, is going to be whatever it was previously. Now let's say you had an input of 1, so the output is going to be 1 based on what a D latch is. If the clock hits 0 while the output is 1, the output shall remain 1 until the clock hits high again, or hits 1 again. Now this is very convenient for the circuit we're recreating because, as you notice, the first light needs to remain on throughout the whole time until all 3 lights come on. So if we can keep the first light in its old state, then we can make the circuit work. And also for the second light also needs to remain in its first initial state until the third light comes on. So this is why we're going to use a D flip-flop, and that's why I explained it as our first component, because it's the most complicated one out of the few we're going to use. So I'm going to explain the technique we're going to use to recreate the system, which is called the shift register system. Now, shift register, what it does is it takes the initial output, depending on how many outputs you have. So I'm explaining in terms of our circuit, which we have 3 outputs for the 3 lights. It's going to take the first output, pass it to the second output, pass it to the third output. Now let me explain it in terms of the timing diagram I have previously. Basically, as soon as the first clock pulse hits in the first second, right here, once it hits high, it's going to take this output and pass it to the second light. So 2 lights are on. And the very following second is going to take that same output and pass it to the third light. So now all 3 lights are on. Kind of like an incurable disease. Pass it to one person, that person, an incurable, contagious disease. You can pass it to one person, that passes on to the next, that passes on to the next, passes on to the next, and so on. Depending on how many outputs you have, it's going to keep on passing it and passing it and passing it. The thing about it is, it doesn't reset. So basically, this disease is incurable. So you can't get rid of it. It's going to stay, the lights are going to stay high for the remainder of the time period. So if you have 3 lights, even after this third second when there are no more outputs, all 3 lights are going to remain high for however long you have that switch on. And this is where our problem comes in. We have to find a way to take that idea but make it reset like how we want it, so it can reset and restart again and count 1, 2, 3, reset, 1, 2, 3, reset. So before we begin, I want to demonstrate how the shift register circuit works. Now I have our presets set to high because they're active low, and what a preset does, it has a higher priority over whatever input comes in or whatever the clock puts in. So if these presets were set to low or ground, the output of this Q would be 1 no matter what. No matter what happens, the output would be 1. And that is the same for all of these D flip-flops. Now for clear, it's basically the same idea, except it will set the output to 0. And we don't want any of these affecting our actual circuit and how it's supposed to work. So I took the initiative to set the presets to high so they won't affect us. And we want the LED lights to stay off. We want them to be on 0 per se. So I set these to work with the switch. Once this switch turns on and sets everything to high, the clear initial setting will immediately turn off. But for right now, we want everything off. So we have it attached to the switch, and while the switch is off and giving an output of low, it's going to have this clear presetting active, and the LED lights will be on low. Now we have our clock input. I set it to 1 hertz because we want to be able to see the actual pattern instead of it just flying by. Anything higher than 1 hertz, the circuit will be flying by, and we actually want to see the actual shift register output. Now I'm going to connect this input to the switch. I'm doing this because once we switch the switch on, it's going to send an input of 1, and so we can run our shift register circuit. This fourth flip-flop is actually relevant to the circuit. This is for our next step, which is the ring counter aspect of the circuit. And basically what a ring counter is similar to a register, a shift register, except that once this output passes it on to the next flip-flop, this light actually turns off. So the first light, once it sends the output to the second light, it'll actually turn off. Once the second light passes it to the third light, this second light will actually turn off. And this third light will loop around, and once it gets its output high and passes it back to the first, it'll turn off. So we actually want that kind of aspect in our circuit because we do need our lights to turn off at a certain point. Once all 3 lights turn on, we need them to turn off. So that aspect of a ring counter, and for it to constantly loop around, we want that involved in our circuit. So we're going to kind of make a mesh of a shift register circuit and a ring counter circuit. But for right now, I'm only going to show you how a shift register works. Now, I'm going to begin running the circuit, and as you can see, none of the lights are turning on because I have these set to active low. Once I turn this on, the clear setting is immediately ended. And as you can see in the pattern, it went from 1 light to the second light, leaving the first light on, to the third light, leaving the first and second light on. But as I was mentioning earlier in the video, as you can see, the clock is still running, and these lights are going to remain on forever. This clock input can run for the rest of eternity, and these lights will just remain on like this, because the shift register just keeps on passing the output on and on and on and on. Like I was saying, like an incurable disease. You can't get rid of it, but it's very contagious, and it keeps passing it on and on and on. So currently right now, I have all 3 outputs attached to a logic analyzer. And what the logic analyzer does, it takes the output or outputs for any circuit and creates a timing diagram in relation to it. So all you have to do is double click it, and it will give you a timing diagram for it. So we're going to reset this, and we're going to run this circuit again. And as you can see, everything is currently low in conjunction to the switch being set to low and the clear outputs being active low. Now as soon as I switch this switch on, you'll see the first light comes on, the second light comes on, and then boom, the third light immediately comes on right afterwards. Every second, as you can see, the lights will turn on. But as you can see as well, they will remain active high for an infinite duration. So as you can see, it's been 3 seconds now and it's still active high. So no matter what, it's going to remain active high. So now we can begin our circuit. Taking the liberty of taking the first 3 steps. The first step I already informed you about was the extra D flip-flop for the loop effect. And to reset our circuit is basically going to be our circuit manager. So you need this 4th flip-flop in here to manage the circuit, and I'll explain to you how it's going to manage your circuit. The second step is to attach this output to this first input, this last output to this first input. Initially, this is going to be our ring counter effect or loop effect that we need so the circuit can loop around and be continuous and be in an infinite loop. The third step that I've done is I've introduced an inverter to the circuit. And I'll put an inverter and I put it in the between the last two flip-flops for a certain reason. And that's to, along with this D flip-flop, to manage the circuit. Now, in essence, this is what's going to happen. This first flip-flop is going to receive an active high input, and then it's going to output an active high output. It's going to pass that to the second D flip-flop, onto the third D flip-flop, and all 3 lights shall be on. Once this third flip-flop has produced this output, it's going to pass that on to this inverter. And what this inverter is here to do is to reset the cycle and give us our 0, 0, 0 effect that we want in the timing diagram. So once that active high output comes out, it's going to come to the inverter. The inverter is going to turn into an active low output and pass it on to this last flip-flop. So as you know, a D flip-flop spits out whatever it takes in. So it's going to take in this active low input, spit out an active low output, and pass it back to this first flip-flop. In essence, it's going to create a ripple effect and turn off this light, turn off this LED light, and turn off this LED light. And once it reaches back to this third flip-flop, it's going to come back to this inverter, and the inverter is going to turn that active low output into an active high output and pass it back into this flip-flop. And in essence, that's what's going to start the circuit again and turn this LED back on, turn this LED light back on, and turn this third LED light back on. Now I'm going to show you the actual problem with the circuit to show you how we're far from done. We may get the shift register effect that we want for turning on the lights, but we want all 3 lights to turn off at the same time. With this format, the way the circuit is right now, it's going to turn off in a shift register format, meaning this first light will turn off, the second light will turn off, then the third light will turn off, instead of all 3 lights turning off at the same time. And I'm going to run it for you just to show you. So I'm going to turn the switch on, and as you can see, we have a ripple effect rather than all 3 lights turning off at the same time. So this is where we bring in our logic and the few chips that we need, the other components that we're going to need to perfect this circuit. So our last step in recreating this circuit is the introduction of Boolean algebra or Boolean logic. And in essence, the way we're going to do that is we're going to use the AND gate chip, also known as the 74LS08 chip. Now, in essence, what this Boolean chip does is it determines whether the 2 inputs that it receives right here are true or false. Now, the only way for an AND gate to output a true output is if both inputs are true, or 1, or an active high input. Let me say this again. The only way an AND chip will give an active high output is only if both inputs are active high. If both inputs are active low, it's going to give you an active low output. If one input is active high and another input is active low, it's going to give you an active low output. And here's why. If something is false and false, in essence, it's false. Therefore, that's why you get your active low output when you have two active low inputs. Now, if something is true and false, that is virtually impossible. Nothing can be true and false. That's like saying you want water, but you don't want water. That's not possible. It's either you want water or you don't. So, in essence, a true and a false statement together is a false statement, and that's why you get your active low output. Now, in essence, this is perfect for finishing off this circuit and actually letting the lights turn off at the same time, and here's why. Once, our problem was that once the first light turned off, all the second and the third light did not turn off at the same time. Now, due to this AND chip, if we attach this active low output to this active high output, based on the algebra, it should immediately make this output an active low output. So as soon as this light is active low or receives an active low input and let's say an active low output, it's going to turn this light off and as well turn off the second light at the same time, because it's receiving an active low and an active high output, because this light is already on beforehand. So because of a true and a false Boolean logic coming in, is going to give you a false aspect and turn the second light off. And we can use this same logic for the third light. If we attach it to the first light output and attach it to its output, in essence, it's going to turn off that third light the same time it turns off the first light. So we have solved our problem of turning off both lights off at the same time. Because once this first light turns off, due to the AND chip, since we have attached its input to the second light and to the third light, once this LED light turns off and receives an active low output, it's going to immediately turn off these two other lights. So now that we've completed the circuit, let us run a real-time demonstration to see if the circuit actually works. So I'm going to run the circuit, and as soon as I flip the switch, voila, we have our 1965 Thunderbird tail lighting system. As you can see, it follows the sequential 1, 2, 3 pattern, and immediately as the third light turns on, all three lights turn off. And this was impossible until we incorporated Boolean logic into the circuit with these AND chips, or the 74LS08 chips. Because both these lights, now the second and third light, are dependent on the first light. So as soon as this first light receives an active low output, both these lights are receiving an active low output at the same time, therefore allowing all three lights to turn off at the same time. Now, as a final step in this demonstration, we're going to attach all three outputs to the logic analyzer so we can get a timing diagram, and to see if our timing diagram matches up with the one we recreated in the beginning of the video. So I've attached all three outputs to the logic analyzer. I've also increased the hertz with a clock pulse because of the timing diagram, so we can get faster results when we run the actual circuit. I'm going to open up the window for us to see, and I shall run the program now. And as soon as I flip this switch, you should see the results happen. And as you can see from this timing diagram, it's running exactly how we had it mapped out earlier in the video. The first light comes on, immediately the second light comes on, then the third light comes on. Once all three lights notice they're on, they turn off at the same time. There is a second time lapse, but that's about it. We have the exact recreation of the tail lighting system from 1965. This video is intended for advanced college timing diagram. And what the diagram is therefore, this video is basically almost a lab. This video is almost in some ways sort of a lab. Um, this video is intended for advanced high school engineering students probably looking for a project, or college students.